In this short lecture, I would like to talk about one of my favorite topics on the planet. This is the subject of Poincare Duality, and it's a suite of absolutely staggeringly powerful tools for the analysis of manifolds and manifold-like objects. So we're going to talk about it in a fairly simple context here, and here is a standing assumption for this entire lecture. So I know we've been calling simplicial complexes K and L, but because I want to focus on the manifold case, and this only applies to that really, I'm just going to call it M for the purposes of this lecture. So here's the standing assumption. M is a simplicial complex with geometric realization being a compact, connected, and n-dimensional manifold. Okay, so this is the assumption, and there's already parts of it that are sort of overkill. Let me explain what I mean. We've assumed that simplicial complexes are always finite. So this part is always going to be okay. This part, the connectedness, is also relaxable. You can get by without it. And you know what? Even manifold can be weakened. So I've made 3 assumptions, but this is just to show you a result. So these are all flexible. Okay, and what do we mean by manifold? By manifold, we mean I don't know, Hausdorff topological space, so that tiny neighborhoods around every point resemble standard Euclidean space of n dimensions. So there's something you could say sort of purely combinatorial that about any such M, which is so any such M has the following property. So first of all, I'm not even going to bother writing the pre-property down. The basic property that I'm not writing is that N must have dimension M. This simplicial complex cannot have an n plus 1 dimensional simplex show up, because there's no way you're ever going to get homeomorphism for something in the interior of that solid n plus 1 dimensional simplex with n-dimensional Euclidean space. You're going to see n plus 1 dimensional Euclidean space, so that's right out. So it has to be an exactly n-dimensional simplicial complex. So every n minus 1 dimensional simplex, so this is not the top dimension, this is top minus 1 dimension that you have, is the face of exactly 2 n-simplices, n-dimensional simplices. So it's going to be difficult to draw pictures of this even beyond 3, but let's try 2, right? So say you have some piece of a 2-dimensional manifold, which consists of all these 2 simplices somehow glued up, and you can see that every edge, like this edge, is the face of these 2 simplices. That edge is the face of these 2-dimensional simplices. And the reason for that, of course, is nothing else will work. I mean, if you have an edge and you had only one sort of 2 simplex sticking up out there, then if you look at that point, a tiny neighborhood will not look like 2-dimensional Euclidean space. It'll look like a half space, because only this part actually has anything interesting. And if you had more than 2, so say you had this sort of setup, then again, that point, if you look at a tiny neighborhood around it, now you have sort of 3 flaps sticking out, and it's again no longer looking like flat Euclidean space. So the point is that each n minus one dimensional simplex that shows up in such an M is the face of exactly two top dimensional simplices. And the point of the next definition is to try and sprinkle signs plus and minus one on all of these two-dimensional simplices so that when you add them up with these signs, all the edges miraculously in their boundary cancel. When you take the boundary of the chain, the end chain that you get by adding all of these up, you get zero. So that's the idea behind the next definition. So here it is. M is orientable over F. So that's the field we're working with. If there exists a function, which we'll call omega, which has, as discussed, the n-dimensional simplices of M as its domain, and it sends them to plus or minus one, which are to be thought of as the multiplicative identity, and it's negative in the field F. So satisfying if you take the sum sigma over sigma, so sigma must be n-dimensional simplex in M, of the number that you've assigned plus or minus one times sigma, this is an n cycle. So you've taken all the top dimensional simplices, managed to put down signs on them so that each of these edges, when you take the boundary, shows up once with a plus one, shows up with minus one on the other side, and it completely cancels and it's gone. So that's the notion of orientability. And if you're seeing this for the first time, you might not even believe that that there exist non-orientable simplicial complexes. But the Mobius band, for example, is non-orientable, sort of famously. It doesn't satisfy our manifold conditions because it has this boundary where things look like this. But but it's definitely not orientable. And if you want a manifold example, the Klein bottle. So if you want counter examples to everything is orientable, just look up the Klein bottle. It's a two-dimensional manifold that is not orientable. Anyway, so we're going to assume things are orientable. And by the way, this whole plus or minus one business is only interesting if you're not working with Z mod 2. So two things to note about this definition are over Z mod 2, everything is orientable, including Klein bottle. So so this counterexample that I've mentioned, you need something more exciting than Z mod 2. So take, I don't know, the rationals, so it's not orientable there. Okay, and what else should we say? This M, if things are orientable, is called the fundamental class. Maybe, so that's the definition, so I should give it another color. It's the fundamental class of the manifold M, and it generates all the top homology. Which is another way of saying that the nth Betti number has to be 1 because the only non-zero object that lives in the nth homology is this fundamental class M that we built with our signs being sprinkled. And so it doesn't really matter what omega you choose. You can flip everything by a minus sign, for instance. You can reverse everything and it will still work. Okay, so that's orientation. There might be slight confusion between ordering of vertices and these plus or minus ones on simplices, but we're not going to talk about ordered vertices. So this is all I mean by orientation. So let's go back and remember our assumptions on M. So it has a geometric realization that's a compact connected N manifold. And I would like to add to that buffet of properties that M should satisfy this orientability. And here is the theorem where the cap product enters in a very, very exciting way. This is Poincare duality. And this says if M is a simplicial complex, that satisfies our assumptions, which were that M is a connected, compact, n-dimensional manifold. And on top of it is also F-orientable. Then the linear map, which I'll call DI, which takes as its input the ith cohomology. So they're linear maps. There's one for every dimension I. So for I bigger than 0, going all the way up to n. The map from the ith cohomology to the n minus ith homology given by, so you take an I-dimensional cochain Xi, and then you cap it with the fundamental class, which is available to you because things are orientable. So this is where it sends a cochain Xi. So this is the image. So let's write that di Xi is that, and you can check because M is an n-dimensional cycle. That cap product is going to bring you to n minus I-dimensional homology. This is an isomorphism. So, which is, these two vector spaces, for instance, have the same dimension. And this is absolutely amazing. So you have to build a lot of machinery to prove this, and we're not going to prove all of this in general. But the point is that this has extremely strong consequences for extremely simple-looking invariants, things that you wouldn't naively, without building all this machinery, you'd have no idea why certain things are true. They are true because of Poincare duality. So let me tell you what I mean by that. So these are consequences. So for M satisfying hypotheses of Poincare duality, we get sort of three things. One is the Betti numbers are palindromic. So Betti I of M is the same as Betti n minus I of M. And the reason for that, of course, is that the dimension of ith cohomology is the same as the dimension of ith homology over a field. So the Betti numbers, Betti 0 is going to be the same as Betti n. That's 1 in this case because things are connected. And then Betti 1 is the same as Betti n minus 1. Betti 2 is the same as Betti n minus 2, and so on. So they if you reverse the sequence of Betti numbers, you get the same sequence back. So it's a palindrome, which is sort of cool. The second thing is if n, which is the dimension of M, is odd, then the Euler characteristic of M is 0. So any odd dimensional manifold that happens to be compact, connected, n-dimensional, or n-odd has 0 Euler characteristic. And the reason for that, of course, is that the Euler characteristic is the alternating sum of the Betti numbers. And when n is odd, then I and n minus I will appear with opposite signs, and they will completely cancel. So they occur in pairs all the way from 0 to n. That's an even number of things. Each one comes with an opposite sign, 1. So when you add them up, you get a straight up 0. And if you thought about it a little bit, so let's assume that n is even, then everything appears now twice with the same sign except the middle Betti number, which is So if n equals 2i is even, then you can no longer say that the Euler characteristic is 0. In fact, we know examples like balls, for instance. Well, not balls, two-sphere, for instance, where the Euler characteristic is 2. So this has the same sign, the same parity, divisible by 2 or not, odd or even, as the half Betti number. And the reason for that is either their sum or their difference, depending on I, is going to be an even number. So, which is the sum of all the other Betti numbers, which remember showed up with the same sign twice. So that's some even number. Okay, so these are some absolutely amazing consequences of Poincare duality. And before I end, there are two things that one should take note of. The first one is that this is an amazing one-way manifold detector. Let me try and qualify that. What I mean by one-way manifold detector, I mean that if someone just hands you a triangulation given in terms of simplices and says, it could contain a billion simplices, we don't know, and says, is this an n-dimensional manifold? And if n is odd and the Euler characteristic of that manifold turns out to not be 0, then you don't have to do any other work. You can just count simplices and say, sorry, this is not a manifold, because the Euler characteristic is not 0, and it's evidently the top dimension is odd. Similarly, the Betti numbers, you could just compute the Betti numbers, which is a purely algebraic operation. And if it's not a palindromic sequence, then you're guaranteed that what you have on your hands is not a manifold. Now, it's not an if and only if. You can have non-manifold things satisfying all these Betti and Euler conditions, but it's still quite nice to have a cheap computational one-way test of manifoldness. In contrast, there are no algorithmic ways to see if something is actually homeomorphic to a manifold. Okay, and the last thing is, I know I said I'm not going to prove Poincare duality, but let me actually try and show you a little bit of a small piece of Poincare's original argument, which is quite lovely. So here, n is 2 in this picture. And so what you really need to do is take an I-dimensional chain and turn it into an I-dimensional cochain. And then, of course, various other properties have to be satisfied. But this part is the hard part. And so imagine you had this sort of thing, this piece of a manifold. And of course, it keeps going because you can't have a boundary. So something has to give at some point. But you subdivide it barycentrically. So, you put in all these baby simplices. So far, we haven't done anything we don't know how to do. We're just subdividing the living daylights, which gets boring, I guess, after a while. So I'm going to stop, I promise. This is not a disease. I can quit any time. Here we go. Okay. And now imagine you had, you're now working with chains of this new simplicial complex, which comes from the barycentric subdivision. And say you had a cochain in the original. So there's, oops, that's too fat, isn't it? Let's reduce the size. Okay, here. So here's a co-cycle. So it's doing this, it's doing that. Okay, and then it keeps going. And you now, so this is a one-dimensional co-cycle, and so I is 1, so you need a one-dimensional chain somehow that's capturing the same information as this co-cycle. And so what you do is you go orthogonally to the through the barycentric subdivision through all these earmarked simplices, and that's going to build an honest chain in the barycentric subdivision. So you'd send this blue mess to the red chain, and So this is sending a one cochain to a one chain. If you had a two cochain, it would just be evaluations on some simplices such as this one. What you'd need is a 2 minus 2, so a zero-dimensional chain to send it to. And that's easy because there is a vertex right in the middle, at the very center of this. So that's where it would go. So you'd send that entire two-dimensional cochain to that vertex. And so that's how Poincare originally proved Poincare duality. Okay, that's it for this week. Next week, we are starting much more modern topics. This was all very classical, and we'll be talking about persistent homology. So I look forward to seeing you there.